So we almost crossed the wilderness and reached, almost reached the promised land. Yeah, so today we will discuss hyperintegers. So consider the ordinary set n of positive, no, maybe not negative, let's include 0 here, integer number. And consider its non-standard analog, which we denote by star n. So what is this? No, let us for now assume the simplest situation that our index set I, which we use to construct non-standard universe, is again n. And then what is n star n? Is by definition the following thing. It is the set of mf, where f from I to n. So it is any function or any sequence with integer terms, and mf is the equivalence class of this sequence with respect to the ultrafilter f. On I. Yeah. Mf, it is a equivalence class. So and the relations and the operations are defined here more or less term-wise. Namely, if you have say mf and mg are in n, in star n, then mf plus mg is after all mf plus g. And you say that mf is less than mg if the following is true. F of I is less than G of I almost everywhere, for almost all I. So for the set of I, which is element of ultrafilter. No, similarly, mf equal mg if f of I equal g of I almost everywhere. No, what is here? mf times g equals mf times mg equals mf times g. Yeah, so it is definition. In fact, we can write, let me write once, that what is mf plus mg. mf plus mg equals, by definition, M of the following plus restricted on the pair FG. Yes?
Is it if M dot M last line?
The last MF. Yeah. So we can always use return to this, and so the all operations are after all reduced to this equals this are reduced to the unique operation, namely restriction of some relation on some argument. Yes, so it is all the same scheme. Now, among the say elements of star n, which we call hyperintegers. Elements of star n. Among these elements, there are the simplest ones, which are standard elements. MF such that f of I is identically equal to some integer n, an element of n. So just constant, or MF, this means that all the sequences which are constant but on the set of measure 0. Almost everywhere, let me write this. Stationary element. And these stationary elements, let me denote these elements in this case. MF is n. So notation, because these elements are in all respect isomorphic to ordinary integers. Yeah. So if you consider the relation between them, the operations, they are the same as for the integer. So in this sense, n is a subset of star n. Or star n is an extension of n. No, okay. So first of all, do we have something beyond these standard numbers or this n? No, I explained already that there exist such elements, namely consider the following element of star n. It is, say, u star n. U equals mf. Where, for example, f of I equals I. Here I is just integer. I, which in this case equal n. Yeah? Just growing number. So first of all, if you consider any, say, m in n, yes, and as such m element in star n. If you consider this, then we have the following, that f of I more than m for all I more than m. Yes? No, obviously this. But the set of numbers which are more than m is all n but a finite set. Yes? And the properties of ultrafilter, I always excluded the trivial case, are that the measure of any finite set is 0. Yeah? So measure of the set 0, 1, m is 0. This means that f of I more than m almost everywhere. So if it is almost everywhere, this means that this number, which I denoted by u, satisfies u more than m for any integer, ordinary integer m. Yeah? No? Okay, this means that u is not element of n. U element of star n minus n. So we considered at least one number, so to say number element of star n, which is not standard. It has a property which no standard numbers, integer numbers have. Okay, this is beginning. No, of course, if we have one number, we can multiply the set of such numbers. Say, consider the number v, which corresponds to mg, such that g of I, say equals to I, almost everywhere. Yeah? It is another number, because g of I more than f of I, almost everywhere, no, in this case everywhere, and this means that v more than u. So this is another number, which is another hyperinteger number, v. Okay, now we can construct more these numbers in still other way. We know that for all, say, m in n, m plus 1 is more than n. Yeah? And this is a formula in our language, L. Yes? And so we can apply the transfer principle. The following is true. Here the constants are n, and the constant is operation plus, and the constant is relation more. Yes? Then we have to write, strictly speaking, the following. For all m in star n, m star plus 1 star more than n. Yeah? No, this continuation of plus, it is extension of the operation plus from integers, ordinary integers to hyper integers, and this extension of relation, they deserve to be denoted by simply plus and more. So we write for all m in star n, m plus 1 more than n. No, in particular, it's not equal to n. So, in particular, we have this number u. This m can be any element of star n. It can be finite or can be infinite. So, if you consider this exactly u, then we will have u less than u plus 1. No, simply, similarly we can write less than u plus 2 and so on. Less than u plus m for all m integer n. Now we can write other thing. The following wisdom, that for any m in n, we have the following. M positive implies that there exists, say, k in n such that m equals k plus 1. Yes? So if you have a number more than 0, then there exists a previous number such that this number m equals k plus 1. And k is, in this case, denoted by m minus 1. In our case, u is infinite, so u is more than, say, 1, because it's more than any integer number. So definitely it's more than epsilon, than 0. So this means that you can write in both directions u more than u minus 1. One moment. I have to write similar formula, which is true in star n by transfer. For all m in star n, m more than 0 implies that there exists k in star n, m equals k plus 1. Yeah? So we have the following numbers. U is our infinite integer, less than u plus 1, less than u plus 2, and so on, more than u minus 1, u minus 2, and so on, in both directions. So we have such a, I would say, piece or block of numbers. And we have the following formula also in the ordinary integers, that for any m in n, there is not true that there exists k in n such that m less than k and k less than m plus 1. So there is no integers between m and m plus 1. We have this rule. No, it is proved by induction, I think. So there is nothing between 0 and 1, and then by induction. So here we can also apply transfer. By transfer, we have the following formula. For all m in star n, it is not true that there exists k in star n such that m less than k and k less than m plus 1. I have to put it in the brackets. Always. Because this negation relates to everything which is written here. Yeah. So this means that these numbers are all the numbers here in this, say, segment of star n. There is no other numbers inside this, I would say, block. Yeah. So this is a block of infinite hypernumbers, integer numbers. Now, if we have one such block, we can have other blocks. Yes? So another block. Of course, it is here 2 times u. No, we can define multiplication because we can transfer multiplication from ordinary integers to hyperintegers. Yeah? Less than 2u plus 1, more than 2u minus 1, 2u minus 2, and so on. So this is another block, and this block is more than this, so any number in this block is more than any number in this, because the difference is 2 times u, is u. Difference between any number here and any number here is 2 times is u plus or minus some finite number. Yeah. Now we have a more important still other block. Because we have the following theorem. so to say, statement for, let me write it in our symbol, for any m in N, there exists K in N such that M equals 2 times K, or M plus 1 equals 2 times K. Yeah? So this means that among two consecutive numbers, one is even and the other is odd. One of two possibilities. Yeah? So this is a formula, correct formula. It holds in the system N. So we can use transfer. For any m in star n, there exists k in star n, m equals 2 times k, or m plus 1 equals 2 times k. No, let me write it more accurately. Sorry. M equals 2 times K. And there does not exist so KL in N. There does not exist L in N such that M plus 1 equals 2 times L. So it is 1 or M plus 1 equals 2 times K, and there does not exist L in N such that M equals 2 times L. Yeah, so yeah. So here the first possibility is that M is even and M plus 1 is odd because there does not exist L which such that M plus 1 is 2 times L. Yeah? And the other possibility is M plus 1 is even and M is odd. So M is not even. Yeah? So to be say rigorous, we have to write this. So this symbol or should be somehow completed by another symbol that if something happens to the left, then this does not happen to the right, or this and back. Yes, so I would prefer next time to write this symbol. Yes, it is exclusive or. Okay, so if you apply this, apply the transfer, we have the following. By transfer, we have the following formula for any m in star n. There exists k in star n such that m equals 2 times k, or exclusive or m plus 1 equals 2 times k. Let me put. Yeah. So it is quite, I would say, non-obvious thing that infinite numbers can be even and odd. Yeah? There is a feature which does not follow from anything. I read some speculations what can be different, what can be infinite numbers, and the author, very respected mathematician, argued that when the number goes to infinity, then the difference between even and odd gradually is erased. Yes, so for very large number, there's no difference between even and odd. Here we have a strict difference. They are not only large but infinite. Yes. Why I need these integer numbers? I need these, I would say, even and odd numbers. It is the following. I given u in star n minus n, so integer, and we use this statement and find w in star n such that u equals 2 times w, or u plus 1 equals 2 times w. Yeah. So we divide u into no, possibly with a remainder 1. Yes, and then we construct yes. So w also is infinite, because otherwise, if w is finite, then u by this formula is also finite. Yes, so if u is infinite, then w is infinite. So, and w is definitely less than u. And w plus k less than u for any k in n. No, because the difference between w and u is of order w plus finite or minus finite. Yes, and it is never zero, it is always more than 0. So this means that we can form still other block of these integers, another block of hyperintegers w less than w plus 1 more than w minus 1 more and so on. So we found still other block. Yeah. No, we can go further. Of course, we can, for any such block, we can, roughly speaking, divide W in 2 or in 3 and have still other block which consists of perfectly infinite numbers, but which is smaller than this. Now, if you have two blocks, suppose we have two blocks, two numbers, u and v, such that u in n star n minus n, v in star n minus n, and u minus v also in star n minus n. Yeah. So we have two such blocks, two such numbers, and then we can find a number so u, v, w, let's say z, z in star n minus n. What is z? It is such that u minus v equals 2 times z, or u minus v plus 1 equals 2 times z. Yeah? We apply the same statement to u minus v, and then, roughly speaking, z is u minus v divided by 2, possibly with this remainder 1.
Sorry.
Yeah.
Why u minus v must not is in n star excluding n?
Yes.
Say if u minus u is always 0, say.
Excuse me? No, suppose this is our condition.
Okay.
So, suppose this. We have already constructed several such examples. Then you can consider the number zt equals v plus z. Yeah? This number, we know that t between u and v, it is more or less arithmetic mean of there, and the difference is approximately z. Z is also infinite number. Yeah? And so we have the following configuration of the blocks. We can consider the block around V, a block around T, and around U. So we took two blocks for U and V and found the block in between. Yeah? Yeah. So what we reached by this example, we can conclude that what is the structure of the set of hyperintegers. structure of hyperintegers. If you go, say, order them by in the natural order, then first we have numbers, say 0, 1, 2, and so on, which is the ordinary numbers. And then you have some some succession of u plus 1, and so on, u minus 1, and so on. Yeah, so let me call this block, denote this block somehow, say xi. Yeah, element xi. Here element xi. Here will be some other block, say eta, and so on. We can say that two hyperintegers are equivalent if they are in the same block. Yes, and then the set of blocks, let us denote it by Greek number xi, capital Xi. Yes, so it is ordered set, ordered by the magnitude. And so what is xi? We have initially one element of xi, which is n. And then we have other element, c, eta, zeta, and so on. Yeah? So here these elements are ordered, but this is an interesting order. In this set of these elements, there is no first term. No first term, because I already construct, if you take any block centered around some u, then you take integer part of u divided by 2, and it gives you another block which is smaller and also infinite. And so here is no first term. Here is no last term, because if you have block centered around u, then you can multiply u by 2, it will be other block which is larger. Yes? It has no gaps between the blocks, because if you have two blocks, xi and eta, there is also always a block, say theta, between them, which is xi centered around u, eta around v, and theta around arithmetic mean of them, plus minus 1 or 1/2. Yeah? So theta is strictly between xi and eta. Yeah? So it is called a dense order without first and last element. Yes.
Just to be sure, we remove n from the blocks, right?
N is block in itself.
But it would be the first block.
It is first. No, of course. N, and then after n goes something, I would say, which is called star n minus n. So n is just one block in this definition, and infinite blocks form this set. Let me write it down. That psi has a dense order without first and last elements. No, we know a lot of ordinary examples of such orders. For example, if you consider all rational numbers from minus infinity to plus infinity, they form also a dense order, because between any two rational numbers there is another rational number, and they have no first and last element. Yes, or real numbers. Yes, integer numbers are not like this, because between two successive integer numbers there is no other. So the order of integer number is different. Yeah, the trouble here is that this set is quite large. Yes, the size of this set, I mean the cardinality, depends on cardinality of our index set I. Yes, because after all, these numbers, hyper integers, are constructed using the functions on the index set, and this index set can be large enough. In fact, arbitrarily large. It is not restricted. It is a set, but arbitrarily large. Yeah. So the size, so to say, of this set of hyper integers can be also arbitrarily large. The cardinality arbitrarily large. So this is one of, I would say, a feature. It's not a bug, it is a feature. It's features of non-standard analysis. So we are not restricted here in size. Yes, please.
Do we know actually, would it be comparable or even more precise than, say, the real numbers, as an ordered set?
Real numbers, yes, real numbers are also a set, all real numbers, also a set, ordered set with dense order without first and last element. Yes, of course. So there is many examples of this. Yes, and here I think the difference is not only in size but in structure. Yes, so maybe different models, even if they have the same cardinality of hyper integers, their order structure may be non-isomorphic of one of the another. Yes. So here I consider one concrete index set, but I don't specify the ultrafilter, and I cannot do it. Yes, so maybe for different ultrafilters we have different structure of these sets. But what I wanted to say next is a very important point. Very important point. So if Xi and if Xi, then it is even more relates to star n minus n. And star n minus, so our infinite hyper integers form a dense set, and then their order is dense without first and last elements. But if so, there is some uneasy feeling, because we know the following thing. The set N is well ordered. This means that for any subset there exists a minimal element. So, in the sense that for any, say, B in A, you have B more than A. It can be equal A, because if it's equal to A, then it's the same element. So there exists A such that B is more, such that it is the minimal, so there is no element which is smaller than this. Okay? So, and here we are itching to apply the transfer principle. If this statement is true in set N, then we can transfer it to the set star N. So, and the transfer says that for any set of hyperintegers, there exists a minimal element in this set. Yeah? So any set of hyperintegers has a minimal element. By transfer, we conclude that any set B in star N has a minimal element. Not in the sense of this, our definition of minimum, of comparison between numbers, which is extension of usual relation inequalities. But if you take B equals star N minus N, then it has no minimal element. Because it was written here that this set has order which has no first element. Yeah. So it looks like a contradiction, but here we have to look what does it mean by transfer. In fact, what I said is a cheap sophism, and if you apply transfer accurately, everything is okay. So we have, at this moment, we have to remind that we are living in a universe U, ordinary And so that n is element of U. All our objects or our entities of our mathematics are elements of U. Even if they are sets, they are also elements. For example, n is a set, but at the same time n is element of the next floor of U. Yeah? And of U, in U. And the full statement is that for any A, let me write, any A also element of U, we have that A subset of N implies that there exists element A in A capital such that for any B in N, A less than B. And I close this. So for any A which is element of our universe,
Since the U is not in our universe, would that be a valid formula in our?
excuse me?
Since the U is not an element of the universe itself, would that still be a valid sentence?
No, U is not element of our university, but A should be element of our university. No, in fact, U is certified into floors. Each floor is already already an element, because it is a set at this floor and element of the next floor. Yeah, so we can restrict it to say first several floors. No, we don't need much. N capital is element of the second floor. Yeah. Yeah. So if you live at the second floor, yes, then you can write, say, U second floor. Yeah. Second floor. Okay. Now, if you go to the non-standard universe, then the transfer principle says that here we should somehow change the constants, not the variable, but the constants. So you can see we have the following. For all A elements of star U2, second floor of star U2, if A is subset of star N is element of star U2. Then we have the following. There exists A is A such that for all B in I'm sorry, B also in A. A less than B. Not strictly speaking, I have to write here this star, but okay. Yes, so this is the accurate statement, because when you write for all A, we have to always to specify where this A on each floor is, or it should be on some floor. Okay. So what does it mean? We know that if A equals star n minus n, what happens in this case? Is it this formula applied to this A? So if this formula is applied to this A, then we have that for this concrete A, we have that there exists smallest element. But we know from our construction, from our previous reasoning, the smallest element does not exist. Yeah? Then there does not exist the smallest element. Of A. So what is the conclusion? Conclusion is that A, let me write, star n minus n is not an element of U. No, of U2 and of any other floor. Because if it were in some other floor, it would be also transferable. Not an element of star U.
It's just a really small detail, and
Yeah.
I think we should have that is not empty, but it
Excuse
should
me?
be. I think we should have that is not empty, but should be all stuff.
Ah. Okay. Yes. So, what does it mean? This means that the set of infinite numbers, infinite hyper integers, the set of infinite integers is somehow is some singular. It has not the same, I would say, status as the set star n. Because in star n definitely there exists minimal element 0, if we start from 0. Yes? But if you consider only infinite elements here, then they don't contain minimal element, which contradicts the transfer principle if we not conclude that this element is not here. Yes, this set is not here. Yes. So we have to write not all subsets of star U. No, even we can write n for any n. Yeah? So it is nth floor. Not all subsets of U are elements of star U. It is not so strange if you recollect how we construct this set. So if you have element of star U, what is this? After all, we have to take a function on the index set I with values, say, in sets. Each set is set in U, in ordinary. Yes? Then you consider the functions such that for almost all I, function has the value in the set I, in the set S number I, yes, or set number I, yeah. So these are all these trajectories which almost everywhere are inside corresponding sets. Sets may be different for different I. So we have a set, this set of each such trajectory. It is a function of I, no, defined almost everywhere, which satisfies this, that it is inside the set almost everywhere. Each such trajectory is also element of star U. No, modular, now then we have to factorize over these equivalences are equivalent if they coincide almost everywhere. Yes? So this set has very special structure, I would say. Not every set of trajectories like this is valid, can be say represented in this form. So we have not if you consider the initial, the ordinary universe U, yes, then it has no logically much more much simpler construction. We have some set of individuals and set of subsets plus individual, then sets of subsets of previous plus individuals of the previous, and so on. Yeah, so it is easy to describe. Here we have immensely complicated, say, inductive construction, or I'll say recursive construction of this. And so, no wonder that some sets which look obvious that they are sets, but they are not elements. Here we have really great case for the distinction between sets as collection of elements, yes, and sets as objects of set theory. So object of set theory is not just any collection of any elements of any nature, as it was somehow supposed initially by Cantor. So sets are also circular things. Yes, for example, set of all groups does not exist, for example. Today we are talking about sets and classes. So set is, say, material thing, set is an object, and class is different. Class is a logical thing. Yes, it is, class is described by some sentence in language. So, for example, a group can be defined in our language, as I already explained. Yes, and we can say that the objects which satisfy this definition are groups, but we don't say that there exists a set of groups. It does not exist. Its existence leads to immediate contradictions. So this means that I have to give a definition. It is the last definition today. So I said A, which is subset, strictly subset of U star, is called internal set if the set A is element of U star. Not only all its elements are elements of U star, but all this collection has also is element of U star. Yeah. If A is not internal, then it is called, how it is called? External. Yeah, so the set of infinite integers is external. Star n minus n is external. Now, it is, no, I will talk a little bit next time. So if A and B are internal sets of star U, then their union, their intersection, and the difference right, they are internal. Yes? No, in particular, star n is internal. Why? Why it is internal? Why?
It's standard, right? Like it's just n times n times n.
Because here it is. Star n, yes, it is not only internal, it is counterintuitively called standard set. Because for any set, so for any element, if you consider this element repeated along all the index set, then the result will be the same element included in our non-standard universe, which is called internal. So it is internal. So if what is about n is internal, then what we have? Star n minus n. So we have this set is internal. If n is internal, then the difference is also internal because of this. Yeah, is also internal. But it is not. Hence, n is external. Subset of star U. External subset. So external, so this means that the word like finite or infinite, it is somehow foreign to this universe star U. It is a universe which does not know our finite and infinite. No, simply it contains a lot of infinite, So for it, there is no distinction between finite and infinite. And this phenomenon will recur time and again, that our very fundamental notions do not exist in non-standard universe. There are different things. But this is the first piece of this non-standard world. So next time we continue and consider non-standard reals or hyper-reals. Okay, let's finish today.